Greeting Earthlings! If you follow the channel, you know that we are resurrecting the Apollo communication system with original spacecraft and NASA ground equipment. In the last episode, we were finally able to get downvoice working, which was a complicated affair. Our receiver had been modified after the Apollo program, but thanks to the awesome notes from our hero engineer Frank Lensberg, we were able to revert it to the original Apollo subcarrier frequency. We also had to enlist the help of my ham radio to extract the FM modulated voice from the 1.25 MHz subcarrier, which was not very elegant nor period correct, but it sure did work a treat. Hello, hello?
Hello, hello.
Hello? Oh, it's working both ways?
Yes.
Alright, excellent. In this episode, we will get rid of the ham radio kludge by making dedicated hardware to demodulate the downvoice, by using a phase-locked loop circuit, or PLL for short. And then, as luck would have it, our NASA receiver will decide to give us a good scare and refuse to lock on the spacecraft signal, which will also land us into PLL issues. So this is a PLL-centric episode and will give us some practice with an important circuit that was originally developed for space flight. So I have my boxes of capacitors and resistors out because I've been trying to make a circuit that extracts the downvoice FM signal from the 1.25 MHz carrier. As we explained in the previous episode, the Apollo downvoice signal, once it has been processed by our NASA microwave receiver, is simply looking like an FM broadcast from the moon at a frequency of 1.25 MHz. So what we want to build is an FM receiver that can lock onto a 1.25 MHz incoming signal. It's very narrow FM modulation, so for that I decided to use a PLL circuit, which is right here. Sorry folks, but to make this video somewhat understandable, I have to start the elevator music a little bit early and explain what a phase-locked loop, or PLL for short, actually is. Well, it is a circuit that was invented in the 1950s to solve the problem of deep space communications. Back then, it was first considered impossible to receive a signal from an interplanetary space probe. First off, you'd need a very low noise receiver because the spacecraft is so far away. We are talking Moon or Mars or Venus or Mercury when this circuit was invented. And to reduce the noise of your receiver, your first move is to reduce the bandwidth that it is receiving to the minimum necessary. That's because anything outside of the frequency range of interest is just contributing more noise. The noise limit of a receiver is proportional to its bandwidth, there is no way around it. So it was calculated that a deep space receiver should have a very narrow bandwidth, say a few kilohertz, around a center frequency of around 2 GHz. That was needle in a haystack kind of narrow at the time. However, there is another problem. Since space probes are traveling quite fast, their carrier frequency is shifted by the Doppler effect. And the Doppler shift is quite large, on the order of 100 kHz for the moon missions, which is 100 times larger than the bandwidth of our low noise receiver. To add insult to injury, the Doppler shift continually changes as the spacecraft travels, or even spins around. It was therefore predicted that making a deep space communication receiver would be impractical unless you tuned it constantly to chase the Doppler shifted frequency with a precision of a few hertz, which was of course impossible to do manually. The solution to this conundrum was the PLL, an electronic circuit that will lock onto and track a received frequency automatically down to phase accuracy. This genius circuit is in everything radio today. Your cell phone is full of them. And our very own ground NASA Apollo receiver uses a PLL to lock on the 2 GHz S-band signal from the Apollo spacecraft, as we'll see in a minute. How a PLL works is pure genius. It's an electronic frequency servo loop. You first need a voltage control oscillator, or VCO. This is simply an oscillator that you can tune with an external voltage source instead of a knob, We have encountered those before. This one has the VCO input, so I'm going to put it to the VCO input. So now the frequency of this is controlled by that. You then need a way to compute the frequency and phase difference between your VCO and the received frequency. This is done by a so-called phase detector, which is a bit of a misnomer. Let's call it an RF mixer for now, because that is the circuit that was used originally and it's the one that's used in our NASA receiver. Finally, you need a loop filter. Its function is to convert the AC signal that comes out of the phase detector into a near DC voltage that can be fed back to the VCO. It is usually some kind of a low-pass filter, but its design can be quite complicated. The mixer has two very different modes of operation. When out of lock, the mixer generates the frequency difference between the VCO and the received frequency. This is then processed by the loop filter, and the resulting near DC output is used to control the VCO frequency. If the loop filter is designed just right, and if the received signal is close enough to the free-running VCO frequency, the loop will tune the VCO towards the frequency of the received signal. So much so that at some point, the VCO will finally match the input signal frequency exactly. Let's see, 200... There you go, phase locked. At that moment, something very drastic happens. The mixer's output frequency, which you recall is the difference between the two input frequencies, now becomes a constant DC voltage. The value of that voltage, called the phase error, depends on the phase difference between the now two identical frequencies, which is why the mixer is more generally called the phase detector. This phase error is still fed back to the VCO through the loop filter, but now the feedback loop will try to keep the phase error constant. Usually not zero, but some constant phase difference. And you can choose to go wherever you want. The VCO is now phase locked to our input signal. It will follow any phase variation of the incoming signal, and as a consequence, it will also accurately track the frequency variations of that signal. You can see that the one on the top is driving the one on the bottom. On our NASA receiver, the PLL lock condition is indicated by the green light of goodness. It's a very good omen when that happens. That's what the mission controllers are referring to when they declare that they have lock after the command module reappears from behind the moon. As a bonus, if the input signal is FM modulated and you are locked on it, the input to the VCO is a direct measure of the signal frequency. In other words, it is your demodulated FM signal. So a locked PLL doubles as an excellent FM demodulator. We will use that property to recover our Apollo downvoice in a minute. Making a high-frequency PLL out of individual analog components is not for the faint-hearted. It is a feat of analog design and RF trickery. We'll see a good example in a minute when we look at our misbehaving NASA ground receiver's PLL. But there is an easier way. In the 1970s, people figured out that if you transformed your signals into square waves, and if you had fast enough logic gates, you could make reliable phase detectors using simple logic and flip-flops. Unlike the mixer-based phase detectors, the digital ones output a stream of pulses of varying width and frequency, which is then averaged to DC by the loop filter. Their out-of-lock behavior and transition into lock can be engineered to make much more predictable and stable loops. So instead of finicky RF circuits, you could just build it in a logic IC. And that is exactly what the classic 4046B circuit is. It contains all the pieces needed to make a PLL up to a few tens of megahertz. A high-gain amplifier to transform the incoming signal into a square wave, a VCO, also generating a square wave, and your choice of 2 digital phase detectors. With this IC, you can make a PLL loop up to a few tens of megahertz without being an analog RF guru, which is why it became so popular, and it is still with us today, almost 50 years later. So that's the first time I used that. It's a pretty neat circuit, but man, the data sheets don't explain very much. That's a 7046, which itself is a successor to the 4046. Fortunately, the 4046 they explain a little bit more. The 7046, it's newer Texas Instruments, and then you know how the data sheets, data sheets now, they're not what they used to be. So anyhow, after trying to follow the explanation I gave up, I just did trial and error. So it's this chip that has everything. It has a VCO and phase detector, except they don't explain what the thing do. They don't give you the formulas. You put a bunch of capacitors and resistors around. You have to find what that capacitor is, and those 2 resistors are for the VCO. Then you have to find what the RC is for the loop filter. Then there's another capacitor for the lock detector. Then you have to do some filtering. Yep, it is still up to you, or me in this case, to hook up all the blocks to make a well-behaved PLL loop. You need to select the R's and C's to control the VCO and the loop filter characteristics. I need to get the correct center frequency, 1.25 MHz for our Apollo voice subcarrier, the capture and locking range, a narrow ±20 kHz, and proper FM audio demodulation, which would not have been too difficult if the datasheet had been well written, complete, and had accurate formulas. Unfortunately, it had neither of these things. So it took me a little while, but once it's set correctly, it works super well. So if you look right now, that's my VCO, and I'm feeding it with something. It's not within the capture range, so it's from over here. My VCO frequency is 1.25 something megahertz, and that's the frequency I am on right now. I'm feeding it 1.14, so it's not locked. And move it up, bump it up, 1.56, 1.7. So I'm at 1.20, 1.21, 1.22, 1.23. There you go, locked. And then now the VCO is locked onto my signals. If I go to 1.24, it's going to switch to 1.24. If I go to 1.25, which would be the Apollo signal, it's 1.25. So it locks good. It's fairly narrow, which is what I wanted. And now I'm going to try to use this one that has modulation. It's not as nice to use as the old instrument. Let's do it. There you go. So now we are locked. Now I can modulate channel 1 with channel 2, and channel 2 I have it set as a 1 kHz tone. So go to channel 1, modulate it to FM. That's what it is. Modulate. How do I turn it on? On. There you go. We have our tone, and it's really the tone I'm transmitting here. It's so annoying. There's just only one button. What's wrong with modern instruments? Dang. So finally, there you go. If I move the frequency here, I'm going to get out of lock. There you go. So it went out of lock. So I'll know exactly. Right, 1.25. And this one has an arbitrary function generator, so I can test it with voice. Yeah, let's go the ARB.
Apollo 12 Houston, try SCE to auxiliary, over. Apollo 12 Houston, try SCE to auxiliary, over.
So it looks like I have made my FM decoder. I can now put it on the setup and get my ham radio out of the loop and see if that works.
Moments later.
Well, it looks like we lost our PM receiver. We have voice up. Hello, hello, hello. So that works. But we can't lock on the way down. It's impossible. And then the static air doesn't work. I look at the footage before we could tune it when it was here. Then last time we turned it on, we could lock it when it was there, and now it doesn't lock anywhere. So I think the VCO loop has died. Oh no, my new PLL for demodulating voice from the 1.25 MHz subcarrier seems to work, but the much more complicated and noble one in our NASA PM receiver that's used to receive the 2.1 gig spacecraft downlink and extract its subcarrier seems to have gone bonkers. You win some, you lose some. If that one's shorted, that would definitely make a phase tag error to 0, and that it will unbalance the whole thing and prevent it to lock. It's my guess. So in the machine, it is.
So it's the 6 from the rear.
And then you give it a little twisty. There you go. Oh, these guys haven't been removed in a long time. Okay.
Alright.
Do some surgery on that one. There you go, Eric, you're missing the reveal. There you go. Okay, I have the phase detector all hooked up and I am feeding it thanks to the beautiful Keysight instrument here to 10 MHz waves, and the idea is that this circuit should detect the difference of phase between the two. This is this beautiful RF magic circuit here. One end is either a signal reference oscillator, I can't remember, comes in here. The other end comes in here. We have two amplifiers and I checked the amplify very well. And then this is the RF magic, the active elements of the phase demodulator are these two diodes. And out here should come a signal proportional to the difference in phase, and then it gets amplified. Here is our amplifier for one signal, I have a probe on it. There's the amplifier for the other signal, I have a probe on it, two transistors. The phase demodulator is over in here, and the output comes out here in that little corner where you have the three transistors, which are the three transistors over here. So we're out of RF here, and I am probing just at the entrance of the circuit on the base, and that's my blue probe. I'm going to vary the phase thanks to my Keysight instrument, and you see how it worked. Went up, and I'm going to go to 180 degrees, and boom, it went down. So it's doing the right thing. It's demodulating the phase with a little bit of ripple that shouldn't be there. So let me check the caps. Okay, so I tested the capacitors, they're all good, and now I'm at the output, which is, it should be the VCO control, and that's the blue line, and it appears to work super well. So not this. This circuit seems to do its thing. So I'll just put it back and see if whatever we did made a difference, but I am tempted to say that it will not. So the phase error comes out of the phase detector, as it should, and the static phase error meter should show it. But it didn't budge. We began to suspect the meter itself, and sure enough, it had a broken wire. I managed a temporary repair with a blob of solder, so the meter should kind of work again. That's progress, but that still doesn't explain why we can't lock anymore. And you can see my big improvised solder repair here, but the tough one is the one underneath. I have to somehow manage to recover that wire at the bottom and right in the middle of the thing with very little access, so I was lucky to get it soldered, and it kind of works. It will have to do for now. Okay, we're back on transmitter 1. Let's give it a try. You right there, it's not. Right here. Okay, I got some wiggles from the phase error meter, which is the output of the phase detector after the loop filter. But it is still not locking the PLL.
More moments later.
Okay, I finally got it to lock with the help of an oscilloscope, because there is actually what they call the dynamic phase error. It's the raw output of the phase detector, which when it's not phase locked will give you a high frequency beat signal. So at first I get nothing because I'm too far off. But then the frequency gets lower, it becomes in the range of the oscilloscope, and lower and lower and lower and lower. And there we go. Now I have something that's almost DC. Actually, I could bring it manually to DC. But this tells me I'm way off. I should be over here. So at this point, if the phase lock loop works, if I close it, it should capture it because we are close. Boom, captured it. Now we have a phase error, which I can follow here, so that's repaired. And I discovered that the in-lock thing is working off the AGC circuit. So if you're on automatic gain, it won't tell you. So you have we probably were locked, but we didn't have the AGC button on. So this thing is now completely off. It should be straight in the middle. We repaired that one. The phase detector works, but this is completely off the FM tuning. Something is drifting in what gives you the approximate FM frequency. I think it's just an indication problem. And this is in this module, the 10 megahertz wideband phase detector. Yeah, we're going to remove it, test it on the bench, and it's fairly simple. It's a filter, 2 diodes, and it tells you on which side of the frequency you are. So my thinking is that we lost one of the diodes. Alright, on the bench it goes. Oh, it's where the adjustments for C10 and C9 would be.
Yes, I saw those there on the top right.
Okay, so you're at the right place now. You just have to find the diodes in question.
Here's our input transformer. Those are the 2 diodes.
Yeah, right there. Okay, we're going to attempt to power up this thing. And then I need to turn on this one. You have to go to parameters, frequency, then you have to select which bit you're going to do. Yeah, it's doing it. Alright, so I'm going one direction and the other, but it's working. Why is our meter not working? Why is my FM tuning meter not metering properly? Going to lower frequencies and it's going down. Going back to 10 megahertz, going to higher frequency, and it's going up. Not only it works, but it's perfectly calibrated. So the circuit appears to work, which tells me, it tells us the truth, and we're not locking at 10 megahertz, we are locking at a lower frequency, which means it's a VCO problem. Okay, we have to test it back in circuit.
Much later.
So I think we got it.
We got it.
So I can still get it locked using my old method, where I look at the beat frequency. At one point it should get to 0. There you go. Okay, and it wants to lock. It's locked. And then I get my frequency meter all the way down. Then we started to look at all our frequencies, and maybe our reference frequency is bad, it's off, so it comes out in the front here. I have it on the 5245, should be at 20 megahertz, it's 19.999999. So it's good. Then we looked at what came at the IF, and it's indeed 10 megahertz on average, but it was all weird looking. And then we were all confused for a while until you switched the key. Switch that key. Alright, and now it's good. Switch the keys back again. What did you just do?
Switching PCM, or switching mode from PCM to norm to key.
Right, so we had modulation on it. When you have modulation, you cannot trust your indication, and when we don't have modulation, guess what? It's all doing fine.
So let me show the key.
Watch what happens to the meter.
Yeah.
As the key's going.
Yeah, it doesn't like it. So now we know what the problem is. We just, when we start it up, we really have to have modulation up completely off, and the modulation over there completely off, if we want to trust that meter. We just have to do one little tweak. We just have to make that one read 0, and that's the module we were just playing with. Nothing.
Oh, there you go.
Yeah.
You went too far.
Too far. There you go.
Alright.
We have the 0 meter. So now, with modulation off, I turn open loop, and I should be able to catch it. Put it at 0. And boom, and it should, ha! Phew! We figured it out. And the meter, this one is a little off because I repaired it and it's a little heavier on one side. So we might want to swap with the new meter while we're at it and see if that works. Faceplate transplant.
Great.
Okay. Now that one works too. And it's actually a fine indicator of the tuning once it's locked. And it also would be an indication of your spacecraft accelerating or decelerating, if we the derivative of the Doppler, basically. Alright, sweet, it's fixed. Okay, now for finally what we wanted to do, we have all our needles in the middle, we are locked. And then I've put my voice demodulation contraption here, 1.25 megahertz. So right now it's not locked because we have no voice, but you can flip the voice button. Hold on a second. Locked. I'm decoding. Talk to me.
Hello.
Yeah, that works. Alright, we have voice. Whew. Good recovered. I was worried for a while.